keep going. Now, other than two of you, I have not had a response to the email about the homework. I can't remember whether when I sent that homework, I suggested that there is a deadline. Uh, so typically, without having to announce the deadline, unless otherwise indicated, the deadline for the class or deadline for any homework is the next class day. Okay, so for example, I sent you the homework for, last Monday. That means it's going to be due around class time, then the Monday following. Okay, which means that the homework that I sent last week was due today, around now. Uh, Given that there might be some confusion as to deadlines and things like that, I'll just ignore the deadline for today, and I'll give you 24 more hours. So the homework will be due at 1 p.m. tomorrow. If you have any questions, please do not hesitate to ask me, and then we can go from there. Okay. I'm going to keep the chat open. So if you have any, if everybody's agreeable to that, just raise your hands, please. Okay, raise your hand that you're agreeable. Okay, I think you've already submitted. Thank you, Min and Ma. Okay, again, if you have any questions, please do not hesitate to contact me. Uh, because we are still waiting for Iman. Just out of curiosity, have you begun to look at the homework? The homeworks will typically be challenging, and that is one of the reasons why you have to start. They will take several days to do. Okay, so as a rule, do not kind of wake up from your sleep on Monday morning and say, okay, now it's time to do the homework. Okay, they're designed to be difficult, but they're also designed to cause you to learn. They are designed to cause you to learn, and therefore you have to make sure that you work on the homeworks as early as possible. All right. So did you? Yes, I did. Thank you very much, Michaela. Uh, yes, and that part is correct too. I think one of you has, you know, asked me some questions. Now, for example, if there are some mitigating circumstances, being ill or an other emergency that you can't get off, then, but for that, what you have to do is you have to tell me, okay? Uh, Not in the middle of your emergency, but you have to tell me when you are available, okay? When you have the time and convenience. So again, welcome, Aiman. Class starts at 1 o'clock, but today we kind of messed up a little bit because I was trying to find the original link. So this time, what I'll do is I'll submit a link and save it as a calendar invitation. Uh, 1 o'clock. Class starts at 1 o'clock on Monday. So again, and Aiman, who joined us a little late, for your benefit, just want to tell you that typically, homework is if a deadline is not announced, that means it's due on the date of the on Monday around class time, right? So I sent you the homework last Monday after class, and it is due today at class time. Now, because there might be some confusion as to the because that if I did not declare the deadline or things like that, then I'll let it go for today, but it'll be due tomorrow at 1 o'clock. If you have between now and then, if you have any questions, do not hesitate to ask me. The homeworks are designed to be difficult. They're designed to be challenging because they're designed to force you to kind of push yourself to learn something which you would typically not learn if I didn't give you the homework. Okay, so expect to be challenged. Okay, let us go to the PowerPoint, and one of the questions that we have is, just bear with me for a second. I'm doing something here. Um, and this is just a something that you want to learn, and that is what is called the FASTA format. Okay, so the FASTA format is something that you want to know about, uh, because very often people have kind of these misconceptions as to what a FASTA formatted file is. And so the FASTA format, it could be about a DNA, or it could be about a an RNA, or it could be about a protein. Okay, what it is does not really matter, but the format certainly does. So if you see here, we have the starting line of a FASTA formatted sequence is this caret, this greater than sign here, and then all the information that you could have about that information, as much as you can, as long as it stays in one line, you can keep going. Okay, you can keep going, and all the information that you can. This is about, as we were talking about olfactory receptors last time, this is about an olfactory receptor, and this is musculus. So some sequence called 613, doesn't matter. Olfactory receptor 613. The name is not important. Okay, so the line that follows this caret sign, you can write as much information as you want. When a software, which is kind of doing, let's say, an alignment of sequences, when that software begins to look at your when that software begins to look at your FASTA file, it's not going to consider it's not going to consider this line in the analysis. It's just going to consider that as a title of the sequence. Now, in a FASTA formatted sequence, you will see the sequence, the file name is .fasta, .fasta, or .fa, or .fsa, or .fas. Okay, all of those are FASTA formatted files. Either one is perfectly okay to use. The important thing, so in terms of, again, in terms of format, the line that follows this caret is, or the greater than equal to sign is, it can be as long as you want, and it's just for information purposes. The sequence that follows, this is very important in terms of, so you can see here, okay, you can see here that that it has to be 80 characters long. 80 characters long. When I say it has to be 80 characters long, if it is fewer than 80 characters, like let's say for example you end your line here and you put a carriage return and the next line starts here, that's perfectly okay. But if it's more than 80 characters long, like if you start typing nucleotides or amino acids here, a software which requires the input to be in the FASTA format will ignore those additional things, okay? Which means it's not going to be part of your analysis, and the resulting analysis is necessarily going to be incorrect. Okay, so once again, let me repeat. This is 80, okay? It cannot be more than 80. So what I typically do is in my text file, let's say if I have to manually create a FASTA formatted file, I do this. I write 0 to 1, 1 to 0, and then I cut and paste 8 times or 7 times, so I get 80. And then now I have my benchmark, right? So then I know exactly I'm using 80 characters. Alternatively, you do not have to do any of that. You do not have to do any of this. Just, as long as it's less than 80, it's fine. Because when the program encounters an end of line, when your program encounters an end of line, it's just going to go to the next line. However, as again, it bears repeating that if you have more than 80, after the 80th character, after the 80th nucleotide or amino acid, it's just going to go on the next line. Okay, so this is very, very important. Now, to be honest, more and more software, as you have text processing programs like Python or Perl or some of these or R, what they do is they can actually look at sequence information, nucleotides, amino acids from a protein or a DNA sequence, and just process it without having to be in the FASTA format. So literally, you can go to a web page and they tell you, and the web page says, okay, cut and paste this file, right? If it says FASTA format, you got to be very careful. If they say just cut and paste, then the program will basically understand, and so this is becoming less and less important. But the good part about the FASTA formatted file is that you can have 25 million FASTA sequences, and it can all be in the same file. And then your program will necessarily process this information. Okay. So once again, I'm watching the chat for the little red dot which shows, because I can't really see the chat thing. Or you can, if you have any questions or any doubts or anything, you can you can just unmute and tell. Okay. And again, yeah, it's important to focus. Now, I should say this is not to make anybody feel bad, but we are doing this class online in a synchronous way. You're being taught this class live as it's being taught. Uh, so it very often one of the criticisms of people is like, well, I like to focus, I like to be in a classroom environment, and sometimes as education has kind of moved along and evolved, there is so much we see and learn that does not have to be in a classroom setting, right? And this class is, and one of the things I do is I record and provide the link to the video, because I want to make sure that you guys know, you guys understand that you can watching the video of something that you may have not understood is reinforcement, right? So, but it behooves you, the responsibility then becomes entirely yours to sit back in your, when you're attending this particular class, do it by yourself. Do not be in a place where you're in a crowd somewhere. This way you can make sure that you're focused, because once or twice some of you didn't were muted, and I heard conversations and laughter, etc., in the background. I can always ask you to mute, but if you're in an environment where there are people around you, then it really hurts your own, it hurts your own learning process. Okay. All right. So that, and then we have what is called translating in the first frame. Now let me go to the website, and let me stay here and get out of this format, and I'll tell you why I'm doing it. Uh, I'll I'll tell you why I'm doing it. So let us go to a resource called, and I have the resource linked, but let's go to that resource. It's a very useful resource, and I've actually been able to publish a paper because of that. Publish a paper because of that resource. Okay, so let's go to. So let's see what I actually do. Click on web. What do I see? Okay, good. I'm seeing the right resource. Okay, so here I'm going to go and type in XPACY, which is a protein resource maintained in Switzerland, or the European Bioinformatics Institute. So it's called Translate. It's a very very popular tool. Okay, and this is a sequence which will translate, and we'll see what I'm talking about. And if you have any questions, feel free to interrupt me. Uh, so I go to this translate tool, and here you will see, and this is very important. If you ever were in a situation where you had a DNA or an RNA sequence, and if you wanted to find out how it translates, okay, in the standard you know RNA to a protein sequence. This is one way to do it. So let's go to our PowerPoint, and let me take this in the FASTA format, right? I'm going to cut and paste this sequence, and I'm going to go to translate, and I'm going to input my sequence in here. Okay, now it says, it doesn't necessarily say in the FASTA format, so I can take this out, and you can play around with this if you say, well, it has to look kind of nice, you know, and you can do that, or you can choose not to do that. Okay, and then it says translate verbose, which means that the moment it sees a start codon, it's going to call it methionine. And it runs into a stop codon, we talked about nonsense mutations last time. It runs into a stop codon, it's going to create space between residues, and then you can have, you can have different options, but let's go with the verbose because that's what is the best way. Now there are other, so what you can't see here, and you can go and do this yourself. This is the standard. It tells you the genetic code, the standard genetic code, and I'll show you this. For example, if you scroll down, there is about 33 different genetic codes, and I'm just clicking on one. You can't see the drop down menu, but let's just go with the standard, the kind of the mammalian vertebrate genetic code. Eventually there's a mitochondrial, like you can click on that, for example. And so I'll just go with the standard because the point is to illustrate a certain point, and I'm going to translate. And when I translate, what you will see is it translates intuitively, right, based on our genetic code. And you see that this is let me see if I can make it a little bigger. Yeah, methionine. And then anytime it pretends it's a stop codon, and then it goes up and it translates till the end. Now this is not a full sequence. Now what you will also see is the translation in, this is the first frame, which means that it takes a sequence and the first codon gets translated, right? And the next codon, so the first 3 nucleotides get translated, the next 3 nucleotides get translated, the next 3 nucleotides gets translated. Okay, so now let's go to our PowerPoint and see what I'm talking about here. Okay, and so when you see this translation in the first frame, this is the sequence I included. Now this is not the same one that I put in the into the translate resource. Again, a very great resource if you ever want to see translation. If you have a DNA sequence, you say, well, what does it look like, and what would it look like as a protein in the standard code, right? So in the translation, what you will see here is it takes the first 3 codons, then it takes the second, third, fourth, fifth, sixth, etc. Right? That's translating in the first frame. Now let's go back to our web page, and you will see that now here it translates in the second frame. Okay, so let's go back to our PowerPoint and see that here's how it translates in the second frame. So remember, this is the same sequence, TAG-ATC, TAG-ATC. But now what happens is when it translates in the second frame, it ignores the first nucleotide and starts translating this way. Okay, so you can see the red lines. It starts translating by shifting by one nucleotide. And so now what happens is what used to be this TAG, what used to be TAG is now translated differently as AGA. So if it translates in something different, you actually get another protein, right? Because it's AGA, it's shifted by 1. So now if I go back to my web page, you will see that if it tries to translate in the second frame, it doesn't translate. You don't get a good open reading frame, right? You have a stop codon and it translates, which is very meaningless because it's what's called a nonsense mutation. If you start translating, then you clearly, with all these stop codons, there is no way you would translate our DNA sequence into a stop codon. Similarly, now let's go back to our code, and then it goes a second, so you see it's translating differently. Now, if you want to go to the third frame, it's actually going to skip the first 2 and translate this way. Now you realize that GAT is a completely different is a completely different, right? And that. Now, there is no such thing as a fourth frame, because the moment you get to the fourth frame, then you will take the first three out and start from here, and that goes back originally goes back to your to the first thing, which is translating in the first frame. So now we can look at our web page, and you can see that yes, when you translate in the third frame, it is translating, you see a little piece of a protein, but because it's looking, first of all, it's looking for a start codon, right? So it's looking for the first methionine, and it doesn't get any, and you see a whole bunch of stop codons in the first frame. Now remember, this is what's called a 5' to 3', right to left translation, and you get a whole bunch of stop codons here, and after the stop codon you really don't get a methionine. So this is also intuitively translated in the second frame, first frame, second frame, third frame. You will see that you get nothing useful. Now, it will also, this translate resource is also really useful, because it will also translate into 3' by 5', which means it will take the reverse of the DNA or the RNA sequence. And again, in this thing, I just put a DNA sequence. RNA sequence just works just as well, and it will translate that way. And here you'll see, yes, there's some regions, but you will see a stop codons, too many stop codons to be important. And then we can look at the 3' to 5' in the second frame, right? So it flips over, and then here you will see something, but not enough to justify a full length functional protein. Okay, so it's important to recognize this. And so you can also do the exact same thing here if you start to translate in the reverse frame. So that's the first frame, that's the exact same sequence which is used to illustrate this. And then translate, 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 and then you have the second frame where you take that C out and then translate TAG, TCG, TGC, etc., etc. And then similarly the third frame where you take the T and C outside and translate AGT. Okay, so this resource is helping you translate in different frames. Now, you might say, well, shouldn't the translation always occur in the frame that I want? Okay, and so now for that I'll give you an example of a paper we actually published. So there was I went to a conference once, and I was a postdoc, and I was presenting a poster, and then there was two French people who started talking to me, and he says, "Oh, you do some computational work, some protein modeling work, etc. Can we ask you a certain question? Will you be able to create a model for a protein that we've been working on?" And I said, "Yeah, sure, why not, right? Let's see what you have." And they said, "Okay, don't worry. After the conference, we'll email you." We exchange emails, and we said, "Actually, they'll send me, and they will send me the protein, the DNA sequence." And when we did the DNA sequence, we saw that it was showing up as pseudogenic. It was pseudogenic. It was kind of like it looked kind of like this, like what I'm highlighting here. It looked at, like something like this, and I was like, this doesn't make sense. So I went back to these guys, and I said, we need, there's something not right. And they're like, no, that's a sequence, we actually worked on that sequence, etc., etc., etc. Something is right, something is it's perfectly okay. And so then and so that's the DNA sequence that they had, and we didn't know quite what to do. And then finally we looked at this resource translate, and we found out that the first frame translation happened to be, actually gave us the intact protein. Now, there were some other things about the protein that were structurally completely anomalous. There was something completely different from the rest of from a typical olfactory receptor. It was structurally different, etc. But we knew from a statistical geneticist that this is what they called a functional pseudogene, which means it was, and then they found out through some studies, some population genetic studies, that it was functional in some part of the population and non-functional in some part of the population. So we almost got the sense that in some individuals this was translated in by a regular frame, right, by the first frame translation, and therefore it was uh, not it was pseudogenic, whereas in some people in whom that particular function was maintained was because it was translated in the second frame. Okay, so we actually got a paper out of it, and I thought that was really cool, and I didn't know anything about this before we did the paper. So this is as an illustration of this. This point is kind of very important, right? So this is again because we are looking at sequences, etc. I think this information is something you need to understand. Okay, so now again, therefore we took at what is an open reading frame. An open reading frame is part of the DNA sequence which translates into a complete, well, sometimes proteins have different sequences. They truncate at one end or the other, but you want something that has a start codon and then a continuous sequence, which actually results in a functional protein. So once again, our definition is an ORF, or an open reading frame, abbreviated ORF, is a continuous stretch of codons beginning with it has to begin with a start codon. Another definition is usually a continuous stretch of codon that do not just contain a stop codon, because that results in what is called a nonsense mutation, and a nonsense mutation basically disrupts the functioning of that particular protein. Okay, and again, an ORF may be defined as a region of a specified minimum size between two stop codons or between a start and a stop codon. So different ways of defining, but it's something that contains a functional a functional protein. Well, we talked about the standard genetic code, etc. And so here is your genetic code, and the next slide also has various different representations of it. And so we'll see, you always look at the first letter, so you see U, and again, because really it's strictly accurate to go from an RNA and mRNA into a protein, because that is the that is the process in terms of the golden rule of molecular biology, right? You have a DNA sequence, it transcribes to a transcribes to an RNA, and then that translates into a protein, right? So the first letter is U, so this would be U, so uracil, replacement for thymine in RNA, and this would be the second, right? So U, and the third would be U. So UUU, UUC, UUA, these two translate into phenylalanine, etc. Right? That is. So again, I'm assuming now that knowing this information, if I gave you a short strand of DNA, not something that's cumbersome, you could manually recreate what translate does. Translate is great because it does this it does this in a automatically, so you don't have to actually do it by hand. If you take my advanced bioinformatics class, which I teach in spring, which involves learning how to program, you'll actually learn to write pretty simple programs which will actually do all of this for you just by doing it, right? So you learn using biopython. So okay, so then there are other representations of it. So here you would start, in this representation, you would start with the central one, that is U, and then you would say, for example, UCU and UCC or UCA, UCG. Again, we're going through the entire combinatorics of it, and all of that, anything that begins with a UC ends in a serine. Okay, and so that's one way to look at it. Another way to look at it, which is very helpful, I mean, it's not easy to see, but again, here is the first code, here is the second codon, and also here's the first nucleotide, second nucleotide, and here's the third nucleotide. Hard to see, but the reason why they have shown you this way is because they're giving you more of that that structural proteomics view, and to say that, okay, well, at the end of this, here's a codon, and for example, you will see that um, uh, G G or GA, two things will give you, for example, a glutamic acid, which is abbreviated, one letter abbreviation is E. I'm not showing this very well because the slides are not is not is not being represented correctly, but I can make this a little bigger, and so you'll see that that it's that is looking at it more from a structural proteomic standpoint, and it's telling you how this translates into the structure of the amino acid, right? So that for example, that if you go with GA, and GD, all of these translate. So anything that begins with a G and an A will somehow translate into an acid, right? So you've got glutamic acid, abbreviated E, and aspartic acid, abbreviated with AD. Okay, so different things about genetic code. Any questions about genetic code? And the reason I ask this is because in when I taught this class in fall, um the first question was just a kind of a 12 nucleotides which would have resulted in a 4 amino acid, and the idea, and you were given the genetic code, and you were told to uh, create the protein from it, and a lot of people got it wrong. So are those white strips a start or stop? No, 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 no. The white strips have, yes, the white strips you can see are stop codons. It just means that, anything is UGA, UGA ends in a stop codon. So that really those are really the white strips that I'm highlighting here are stop codons. Okay, anything that ends in a methionine is really the start codon. I mean, it can be a start codon, it could be a methionine in the middle of your sequence, but yes, those white strips are both stop codons. Now, maybe you knew or didn't know this, and I didn't know this until I began looking at the different genetic codes, and just have to understand that there is no universality about stop codons. What could be a stop codon for one genetic code, and there are 33 genetic codes, I think, for different things, insects and archaea and protozoa and things like that. Uh, and then especially then there is also there is a mitochondrial component to the genetic code. When you add all of them, I think there are 33 genetic codes. So a stop codon for the typical standard genetic code with a mammalian vertebrate is not necessarily the stop codon for something else. Okay, so just keep that at the back of your mind. Yes, so to answer your question, Michaela, they are the stop codons, and that's why you can see the white strips end in nothing, right? They end, both these white strips end in no amino acid. So those are stop codons. And there is the tool that I wanted to illustrate. Oops, that's the tool that I wanted to illustrate. And these are, ooh, what am I doing here? Okay, the tool I wanted to illustrate, and and that's the resource I wanted to talk about, and I kind of did that. So let's see here. Okay. All right. The next thing that we are supposed to look for is BLAST. Okay, and BLAST is an acronym, right? And again, you may or may not know this, but the difference between an acronym and an abbreviation is when you take that abbreviation and it let me move me a little bit down, and if you take that abbreviation and we and you it actually sounds like a proper English word, and that is so. And every acronym is an abbreviation, but every abbreviation is not an acronym. Okay, so BLAST is the abbreviation actually sounds like a word in and of itself, which is always easier rather than say BLAST, right? And you can see the full form is Basic Local Alignment Search Tool, and that is where the alignment comes from, and that's where the acronym arises from. Okay, so again, you're learning something different, and that is what is the difference between an acronym and an abbreviation. So an abbreviation that sounds like an actual word, like in this case BLAST, is an acronym. Okay, now there are different BLAST searches, and again, remember when you talk about blast searches, and the reason why the progression of this class, even when we go up to next generation sequencing, the progression of this class always builds on knowledge, right? So when we talk about alignment, right, we are doing alignment like we did, where gap penalties are considered, distances are considered, the alignment is considered, the use of Needleman Wunsch or the Smith Waterman is considered. So all of these are used in BLAST. Now, typically, because BLAST is a web resource, you can just say, well, I'm not even going to worry about it. And I probably, most people don't even teach this anymore. You just dump it into a web program and you get the results that you're seeking. Okay, so there are different kinds of blast, and now they have like genome level blasts, and every time you go to NCBI, the resource, you'll get a different kind of blast. But these are the foundational blasts, and there are six kinds of blasts. So let's see what they are in terms of the definition. So if you have a protein sequence, and what does blast mean, right? Again, we blast it is basically it goes and aligns sequences to find something that's similar. Remember, the foundations of what we're looking for is that you look for something similar, you look for something orthologous, you look for something paralogous, and the reason why you're doing it is to find, to take an unknown and then you align it against something that is known, and you say, oh, that aligns really well, it is similar or it's identical. That means, and if it aligns with something that you know, that means it is the same function, it might come from the same species, it might have some evolutionary characteristics that are identical, and that is one of the reasons why you use BLAST. So uh, let's see, so BLAST P. So if you have a protein and you want to know more about that protein, what it aligns against, what the BLAST P will do, will take a protein sequence and it'll align it against a database of proteins. Okay. Now, if you have a nucleotide sequence, right? If you have a nucleotide sequence and you compare it, you take your nucleotide sequence and you compare it against a big, gigantic database of nucleotide sequences, that's called BLAST N. So BLAST P, P for protein, BLAST N, N for nucleotide. And then you have more combinations of things, right? So let's say, for example, and this is important because we learned about, the first frame translation, second frame translation, and the third frame translation. So if you have a situation where you in BLAST X, what do you do in BLAST X? You take the nucleotide sequence of interest, right? You take a nucleotide sequence of interest, then you translate it in frame 1, translate in frame 2, translate in frame 3. And the reason they call this a 6-frame conceptual translation is, so the first 3 are 5' to 3' translations, right? Frame shifted. Then is 3' to 5' frame shifted translation. Then you run it up against a protein database. Why? Because you've done the translations and all the things. So now you've got every possible combination of possible protein that arise from that nucleotide, and then you run it up against a protein database, kind of like BLAST P. Now, do understand, therefore, that you take from one nucleotide sequence, you end up with 6 protein sequences, so it's going to take 6 times as longer, right, than a typical BLAST P. Then you have a T BLAST N. So then what happens is you take, which is even longer. So now you have a protein sequence and you say, okay, that my archive, my database of, I'm going to take all of those DNA sequences and I'm going to do a 6 times or a 6 frame translation of all those. and then I'm going to take my protein sequences and go to and compare with all those protein sequences. Okay, and the reason why you need that, especially when you want to compare proteins, is because your standard single frame translation somewhere, and I gave you an example of how we were able to publish an entire paper, that somewhere there might be, because of a frame translation, there could be a protein hidden in a second or third frame translation that we are not immediately aware of. Okay, so T blast N is that. Then you have a T blast X, which you have a nucleotide. Okay, you have a nucleotide, and you do the six intuitive the translation, the frame conceptual translation, and then you compare it against the entire archive, which is, and I think about how many billions of nucleotide sequences are sitting in the archive against which it compares. So you take your thing, do it 6 times, so you multiply that by 6 times, and then you take your entire archive. That means you do your T blast N, right? And so can you imagine from a standpoint of how long it typically takes to do this? Now, why do you do this? Because your typical go-to methodology would be blast P. Okay, you have the protein. Well, the next easy one is, well, I don't have a protein, don't care about the protein, I'm interested in the nucleotide sequence, and you say, I am going to do a blast N. When your blast P and your blast N don't work is when you say, well, I need to see that then there might be hidden in this um, a protein that's not immediately obvious because I'm not doing the translation that nature has already done for that particular protein. And then you have what is called blast. Okay, so you get the point of it, and I'll just reiterate it for a few seconds. So then in blast is an iterative process. So let's say, for example, if you have a protein that you absolutely cannot find anything about it. So what it does is it takes a sequence of interest for you, a protein sequence of interest, and then it looks for related proteins, and then it comes up with a composite of that protein, and then you're going to basically go take it against a protein database. And this is for proteins, where you absolutely cannot find something for distantly related sequences. They're distantly related, so they might be related structurally, but not necessarily sequentially. And that's where you're going to create a composite of kind of known proteins. So you're really not there is not a single protein that you do, but you create like a composite, something that is a kind of a resultant protein which itself takes the effort, and then you run it against something. Again, in addition, there's all these genome blasts and all of the additional things that happen. Foundationally, it's the same. And again, going a little back, a couple of steps back in last lecture, so everything it does, the alignment using Needleman, Wunsch, or Smith, Waterman, depending on how it determines the sequence to be, it does the gaps, it does the penalties of the gaps, it gives you scores and all of that. So all of the things that we learned last week is actually being used by BLAST. So if you think, well, I don't really know, what it really does, at least at a conceptual level, at a foundational level, say that, oh yeah, I learned all those things. Yes, the BLAST web page is the black box to me. It's just I throw something at it and it spits a bunch of results out. But do understand that at the back end, it's doing something different, right? So once again, you take a protein sequence and you run it against a protein database. It's called BLAST P. You take a nucleotide sequence, you run it up against a nucleotide sequence in aligning, and that's called the BLAST N. If you have a nucleotide sequence and you don't know anything much about it, you take that nucleotide sequence, translate it using a 6-frame translation like we've seen before, run it up against a protein database. In T-BLAST N, so that's BLAST X, in a T-BLAST N, you take a protein sequence, but in this case, you do a conceptual 6-frame translation of everything in the archive, and you do that comparison. In T-BLAST X, you have a nucleotide, you actually do a 6-frame conceptual translation of the nucleotide of interest, create 6 proteins out of it, and then you go into your archive and create 6 versions of the archive depending upon the protein. And again, I'm sure there are other little caveats which say, well, wait a minute, if you have all these stop codons in the middle, like we saw in the case of in the use of translate, we will throw that out the equation. So this way, you're not just grinding away when you know you're not going to get results of anything. But you can see how typically long that would take. Now, you also then take into account that NCBI at any given time there's 25,000 people accessing the BLAST resource, and so again, a lot of people, they come to a master's program or a PhD program, and they say, well, I've had undergraduate bioinformatics, and typically the experience that they'll immediately relate to is a BLAST search. But this is something that is a little more. Now, if you have a protein that's not really cannot be found because the sequences are distantly related, but there might be something about the structure or the function, then you bring a group of proteins together, create a composite, and then compare that to the protein database. So that's SciBLAST. And there are other kinds of, again, they use BLAST, the foundations of BLAST, in many other things. Okay, so let's go to this resource, and it's a simple matter, for example, of going to a resource and then just typing in BLAST. So NCBI BLAST, and that should typically do it. You don't have to necessarily remember everything. Okay, so there you go. The BLAST is the BLAST, the basic local alignment search tool. And I'm going to, so you can see that they've even made life a little easier for you. So they have a micronucleotide BLAST. You can actually download BLAST. Then there's the human you can do. Then there's something called mega BLAST. Sorry about that. And then you can have a mega BLAST, and all different kinds of blasts. BLAST N, as we can see, the nucleotide BLAST, different executable. Now, you could, let's say, for example, you have to blast many sequences, right? They allow you to put an executable version of BLAST on your local machine. This way, you don't have to go over the web, and it takes forever, especially during busy times of the day, like maybe this. And we'll see an example of that at a busy time of the day, and therefore it's hard because the web page, and it takes forever. And if you've got to do 25,000 of those, then that's not going to be feasible at all. Now, in my advanced bioinformatics, and I'm not necessarily I'm not including this as a teaser that you should take my class. It's just that it actually teaches you how to do this. But you can have an executable BLAST on your computer, which means they will allow you to download that database archive, right? You can do this. So this way, you can run BLAST day in and day out and not have to worry about the web or the connectivity, or do I have a good internet connection, etc. You can do that. Now, but then the problem with that is you have to update, because remember, people are constantly supplying nucleotide sequences of different species, etc., which means you actually have to literally weekly update your BLAST archive, the database. You have to update it to make sure that you're current, and of course, which means that you're going to have a lot of storage space and processing speed in order for that to happen. But again, if people are going to do many blasts all at the same time, that is what they see. Now, one of the things that people need to know in BLAST is what is called the expectation value. So every time you have an alignment, you're the sequence that you provide, the sequence for whom you're trying to find something, you have, and then you compare it to another sequence. You have to have an expectation value, and the expectation value is very important. And when we actually do a BLAST search, we'll see what it means. So the expectation value is important, because the definition is, again, so before that, let me qualify all of this by telling you that the lower the expectation value, the better. It's kind of like a golf score, right? When you play golf, it's like how far and how fewer strokes can you get to the hole is better, because that means you're a better golfer. So the expectation value is low. And what does it mean? An expectation value, every time there's an alignment, an expectation value is calculated. Okay, and the expectation value it tells you what are the chances of those two things that you aligned and that got that the web resource gave you, what are the chances that it is random? Okay, it's just because of a random match, because something is being mapped against, is being aligned against, 25 billion other things. Is it just, did the result give it to you as the result come back to you as, and is it random? So the expectation value is a measure of the randomness of that particular alignment, which means that the lower the expectation value, it means, oh, this is actually, this alignment is actually a true match, that there is actually, and not, and you didn't get the results because it was purely at random. And I think that is, and this is the part that's crucial and needs to be understood. Okay, so once again, lower the expectation value, the better it is. Okay, so let's keep going. Okay, so now let's go to blast, and we'll go to that same sequence we looked at before. Okay, so this way we have something. Oops, 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 oops. So I'm just going to take this sequence, and again, now you know that we can go to NCBI blast, and that's a protein sequence. So we'll just go here, and there, this will, you see the blast X, the blast N, the protein blast, nucleotide blast, it's all right here. And then there's other things, smart blast, primer blast, global align, CD search, immunoglobulin blast, vector screening, CDR, multiple alignment. There's all these interesting things that you can do with the blast. Then again, remember how I told you, you can download blast, okay, and use the blast, that's it's a interface, and you can also use blast in the cloud. So there's all kinds of things. So let's go to protein blast, because the sequence that we have is a protein. Oops, never mind. Let's go to nucleotide blast, obviously, because the sequence that we have is a, now alternatively, you can so let's do this as best we can, and let me show you all the features. It's a little too big. Okay, so that's the sequence. And then, or alternatively, remember in BLAST, I told you that you can put as many sequence as into a one FASTA file, okay, and the extension would be FASTA or FA or FA, FSA or FAS, okay, one many things, and then you can give it a job title, because depending on how long you expect that process to last. And then typically what happens is, if you have a very long sequence, if you put an entire cosmid in there, right, or an entire chromosomal sequence, you can actually, rather than say, you can say, rather than say, oh, I have to sit there and wait and look for the sequence, and what number to what number is of interest, that means where there is an open reading frame that needs to be translated or so. Then you can say, I want nucleotide number 550 to 850, something like that. Okay, so it already found out, and the reason it found out the job title was because it already looked at the sequence, the title of my FASTA file. And you can also align two or more sequences, so you can use BLAST, but the technical aspect of BLAST, by actually doing what is called a pairwise alignment. So if I clicked on this, then it would show two different ones. And then you can say, I'm standard databases, RNA, ITS, genomic transcript databases, beta coronavirus. You can basically click on any of these things that you want, or all of these options. And again, you see my mouse moving, but this is just a drop down menu that you cannot see. And then you can exclude organisms. So let's say, for example, I wanted orthologs, and last time we know the definition, same function, but which comes from a different species. So let's say, for example, this is mouse, right? And I said, honestly, I do not want any comparisons to other mice genes. I just want everything else. So you can actually, or you can say, I just want, or you can also say, I don't want any, I want humans and nothing else, right? You can also click exclude, and then alternatively, you can add organisms to exclude. Okay, sequences from type. This is, you can choose this. You can create a custom database, a YouTube link to tell you how to do that. And then you can also change it and ask for highly similar sequences, or I want more dissimilar sequences, or somewhat similar sequences, so I can go with somewhat similar sequences, and I can show results in a new window. And that's basically, so there are various options that you can use. And once again, these are the blast P. Remember I told you T blast X, T blast N. Sci blast is also available. These are the standard. Either it translates into a 6 frame conceptual translation, and then does the blast. It takes that much longer. So we'll just go with whatever we have and play around with it. And there are things like algorithmic parameters, that you can actually say that I want an expectation value, I want an alignment of a particular type. And here, remember you can go with your match score, mismatch scores, gap extension. See, gap extension of 2. Now you're beginning to understand this. Now, typically what most people do is they say we don't want to be worried about any of this. But if you really, now if you, like somebody like you, because of last class, you have to have a foundational understanding of what any of these things mean, right? Expectation value threshold. Well, you can change this and say it has to be less than 0, or this 5 times 10 to the negative 2, right? That's what that number is. Okay, this is the alignment, how many words have to match. Okay, how many words have to be when I say words, it means how many nucleotides or amino acids have to match. Again, all of these are options that you can add into it. And again, you can say, well, because eventually it's going to give you an alignment score, remember, and that happens. So you can just say I want I want a match of, if it matches I want a score of 1, if it mismatches I want a score of -2. So the default is -3. And then you say, if you want to put a gap, you can also make it harder for the gap, which means you can say if there's a gap I can make it 11, which is what we did when we did when we did the exercise last time. And then if you want to extend it, so there are all kinds of options, right? Uh, like, so sometimes it might be you'll see that if you went to this place, you would say that existence 0 extension 4, that don't give me a penalty for if I introduce a gap, but if I extend that gap, then include a penalty. So there are all kinds of options. But again, now because you're familiar with these concepts, because we looked at them, you'll be able to look at them. But mostly most people won't even look at that. They will just say I just want to blast. Okay, and that's what we're going to do. You click blast, and then let me see, you wait around. You wait around a little bit. So now what it's doing is it's going to tell you times in submission, 7 seconds, it said 9 seconds, etc. It created a kind of a request ID. It's updating the page in 3 seconds, and it found something for you. Okay, and there are other things that we can do. And it also because it provided an ID for you, it's also storing your information. Okay, and here's what we see. Now there are many different things that you can see. So we said musculus, and we never really excluded a mouse. So you figure you're going to get a whole bunch of mice genes in here. And it says, it aligned with a taste receptor, which is kind of like an olfactory receptor, depending upon what you're looking at. It found something from a clone, then it found an olfactory receptor, then it found something from Cancer Institute. And again, you can use the resources to basically customize your search. So then you can see it found a predicted match with an Arvicanthus nilo Nilocticus, then Rattus, okay, that is there. Then Muscaroli, which is another word, another kind of comes another genus of mice, okay, and you get many, 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 many different things. I think the first 100 now. And now we'll see some additional stuff, right? So now this tells you what the species is, and if I kind of clicked on it, it'll tell you what the uh, the subspecies that are. So you get a whole bunch of subspecies for mice, and then right up to its genus, it'll tell you what the evolutionary breakdown is, right? It's going to tell you the family tree, starting from eukaryotes, right, multicellular organisms, right to metazoa, to all of these things, right up to right up to the genus. And then here you've got, the species is musculus, and then you see the whole bunch of subspecies. Wherever possible, it's trying to give you where, Japanese wild mouse or West European house mouse or Southeastern Asian house mouse. So all of these are. So here's what it's going to give you, but that's not the result we are looking for. And so again, all these are different species. So a lot of stuff. The first 100 results came to you. Now let's look at let's look at something else here. Now this is the alignment score. Okay, and this is the total score depending upon the complete alignment. Now this is like the query coverage means, this was 100%, but how much of the entire species, the entire this thing was actually aligned, so it's 97%. This OR613, this is the our original query. Okay, so number one is original query, and then you will see, the percentage changes, 97, 86%, etc. And then I told you about the expectation value, and the expectation value, it's you can see the e value, that is the one that is highlighted, and what it's trying to do is it's actually telling you that 0% chance, at least the first 40 or so, 30 or so, have 0% chance of it being a random alignment. But even the others, right? You can see such good. It's like 6 times 10 to the negative 6 times 10 to the negative 138, which is an extremely small number. So you can be pretty sure that this is actually pretty solid in terms of that these are not some random alignments. Okay. Then in terms of the identity, you will say that this was 98.84, so almost identical. And then this is the length where it compared against, against what length. So for example, this was obviously a complete sequence, or probably a chromosomal sequence or something like that. I don't know for sure, but you can see it's it's 140,000 nucleotides. So that's the length of what it measured against. And here's the accession number. So if you want to find out more about this, you can go back to its, so it's not a, it, you can go back to its original, entry. So this is a clone complete sequence, and this tells you more. So you know exactly where this thing came from. And here's the whole sequence, right? That's what it's 140,000 something something, and so that's the part which was accessed in terms of the comparison. Okay, and so then what you can also do is you can look at it in a different way. You can look at it in the graphic summary. So the graphic summary says that if it's greater than aligned is 200, then less than 40 sequences aligned, then that's really bad. But here you can see, because the alignment is so good, expectation values are so high, you can see that. And some of these are means that the entire length was not looked at, right? And so this number one is our original. And actually you can literally click on each of these numbers. Okay, so I'll show you something. Okay, if I push this up to the bottom of this, okay, to the bottom of this, and if you mouse over on this, it'll actually tell you what the result is. Okay, so you can see that all these alignments are very good, right? Very good, and that's what the red color is. So that's a graphic alignment. You can go to the actual alignment, and so this is the sequence of what part of the number. So this is obviously the sequence with itself. So you're going to get 100% alignment. And then, for example, this is against that big clone, the complete sequence. So it tells you it aligned on a certain part of it. So this was 9%. It went from nucleotide 9. This is the query. This is the one of interest, to 520. Oops, 9 here. Sorry, 9, the one I've highlighted, to 527. But in the big clone, you went from 85,415 to 85,933, right? See, 85,933. So it's not just they have to be the same size. This query sequence of yours is going to be sent up and down everything to see where that alignment is going to take place. Okay? And you can see. So what else can you see? So for example, you will see that if there is a match, you'll see a line, right? The G and the A and the T and the G and the G, they match. But here you see there's a G and then there is a C. So that is not aligned, and therefore there is a gap. No, it's not a gap, sorry, it's just a mismatch, right? And so you can see there are no gaps. Oops, there are no gaps. No gaps have been introduced here. And plus plus means it goes from 5 prime to 5 prime, 5 prime to 3 prime, 5 prime to 3 prime. And then it says that this is identities. That means there are 479 without gaps, 479 matches. Okay, and then then so this is based on expectation value. Now let's go back to the, again, if you have any questions, do stop me, and we'll, so for example, you can go back to the description. That's the original thing we looked at. And then you can come here to the top and you can say, I want to identify, as you can see here, that it's 100% is obviously with itself, and you have 98.4, and then you have some in the 80s, right? And you have 80s, and then it goes, so that's the percent identity. And so you can say I want percent identity to go from 95 to 100. Okay, so that'll take away, and then when you click on filter, you will see now that you have far few, right? The from 95, you said 95 to 100, you're going to have a far few. So this way you can be sure you're really getting, if somebody told you just find the top 10, the top 5, this is not just, you don't just click and pick the top 5, it's based on e-values. You can also do other criteria, right? You can also do query coverage, right? So if I say I want only the query coverage, so I take this away, right? And the query coverage is from, let's say, 95 to 100, okay? And I can filter, and then I get the results, obviously a lot more, but alternatively I can just say I'm so confident in the results that I'm interested in that I only go from 0 to 0, and I filter, and that means I'm only going to get the ones which are, well, I mean, even these are basically close to 0. So there are other ways in which you can do this. There are different ways in which you can see this, and clearly you'll see something else, that this expires. This expires from on at 3 o'clock in the afternoon on the 25th. So we've got a couple of days, right? So if you save that ID and put that ID, this information, you can also download everything. Okay, so I hope this was a kind of, will give you kind of the nitty gritty of a blast search. And of course you can play around with it and do other things with it also. All right, any questions? Okay, if there are no questions, we will we will keep going. Now, there is something else called as BLAT, okay, and we will look at what BLAT is. So the BLAT is, it's basically alignment, just like BLAST, okay. It's not sequence, but it's alignment, and we'll see now. How many of you, show of hands, know what the genome browser is? the UCSC genome browser. There are several genome browsers, okay, Michaela, one of you. So there is a genome browser, and we look at the genome browser the next in the next time. And so you have, in terms of the genome browser, you have the genome browser, and then there is the most popular one is the UCSC genome browser. Other genome browsers, NCBI has its own genome browser. When you look at the gene when you click on the gene choice as opposed to the nucleotide choice, you'll get a genome browser. You'll also get a genome browser from Ensemble, which is a European Bioinformatics Institute's genome browser. They all do things that are different, but the UC, University of California at Santa Cruz, has a genome browser. So it's part of, under the auspices of UCSC, that they have developed something called as BLAT, which is maybe not a comprehensive, but it's a version of BLAST, but a little less comprehensive. But if you're looking for efficiency and quickness, then BLAT works just as well. So let's see what BLAT is. Okay, so let's ask our questions. What is the difference between BLAT and BLAST? So BLAT is an alignment tool, local alignment tool, just like BLAST is, but it is structured differently. For DNA, BLAT works by keeping an index of an entire genome in memory. Okay, so typically this is restricted to certain genomes whose genomes have been published. So thus the target of BLAT is not a set of GenBank sequences, right? And GenBank sequences, when we said, oh, I take my protein and I go and blast it, or I align it against data, against a database, that is what it is, right? So the target is not a set of GenBank sequences, but it's an index. So what they do is they take an entire genome and they break it up into 40 nucleotide sequences. And so when they compare it, and of course that is then attached to whatever sequence identifiers and things like that. So when you take your sequence and you align it, it's not aligning to everything that NCBI has. It's only aligning to this particular index. Okay, so index of the entire genome. By default, the index consists of all non-overlapping 11 mers. So it breaks this up into pieces of 11, except for those are heavily involved in repeats, and it uses less than a gigabyte of RAM. So because it's not going up against everything, it doesn't take a lot of processing speed. This smaller size, so basically it says if this 11 sequence is matched really well, then it's a good chance it comes from that particular sequence. Okay, BLAT is far more mirrored because it does not have, you're not going up against everything. Again, the processing doesn't take long. It's a lot easier to store store an indexed version of a genome, right? And what is an index? What is an index? So think about it. Think about it this way. At the end of a book, you will typically have an index, right? Granted, at the beginning of a book, you will have a a table of contents, right? And so if you want a general idea of the contents, what will you do? You will go and you say, okay, this particular thing looks like it's in chapter one. But if you actually want words or phrases specifically where they occur in your book, what do? You say, I'm going to go to the back of the book. I'm going to look at my index, and the index will tell you exactly what it is. So when you have an index of 11 mers, okay, an index of 11 mers, then it's almost like saying, well, I want to find that. So where do I find a good match for this 11 mer? And that's the way to look at it. Okay, so BLAT is designed to quickly find sequences of 95% greater similarity of 40 because again it's matching against something very limited. It may be miss more, so again it may miss more divergent or shorter sequence alignment, because if it's less than 11, then you're not going to find it. And the default settings, are slightly different from the graphical version of BLAT. So again, so the UCSC genome browser, if you want to do a search, it actually uses BLAT, and they have access to the various genomes that are available, and so they can do it a lot more efficiently. So the foundational idea is still the same. It's just that the execution is slightly different, because it's almost like saying, look, it's like saying, like a Google search, right? And again, I don't know the ins and outs of a Google search, but let's say any search engine. What happens is, let's say if you were told, okay, and this is a pretty good analogy. What if you were told, go to a web page related to Chiquito Crasto? Okay, you type Chiquito Crasto. Now, one way would be to go with all 25 trillion web pages, right? 25 trillion web pages, and take the word Chiquita Crossrow and look through all the web pages. Alternatively, if I took every web page and I just made it into, kind of words which define it, and that's what we use when we create meta characters and meta words and things like that for every web page, so that a search engine can find it a little more easily, right? And let's say then you take your web page and say, no, I'm rather than let it search through the entire text of everything, I'm going to create an index, a word list of the, a word list associated with that particular web page. Now what happens is, rather than waste time and resources going through all the content, it just says, well, does it match those particular words? Does Chiquita Crossrow match any phrases? And there will be one or two web pages where it actually matches the phrase, and then the search engine is going to return that. It's the exact same way. If you create these things of 11 MERS, then you can basically say, oh, my stuff is in there, and therefore I know exactly what gene, for example, to go through, or what sequence, assuming if it's a non-coding region or something like that. Okay, so that's the difference. But that doesn't mean that every time you do something, BLAST goes to all 350 billion sequences. No, they probably also have a little more efficient. With BLAT, what happens is, because they are restricted to specifically to genomes, and genomes that have been published, and not every sequence that ever been dumped for whom a genome is not available. It's a lot more efficient, right? And so again, you can just say, well, what is the BLAST database? Well, the BLAST database is probably a few gigabytes. Most people with, for terabyte of hard drive, can be able to keep it on there, and therefore the processing speed and the storage speed is not that much. So is it absolutely comprehensive? No. But is it functional enough if you want to stay within a particular species whose genome is available? Yes. Okay, so once again, we'll go through this. The BLAST finds regions of local similarity among nucleotide amino acid. It compares a query sequence to a large set of sequences. That's the target, and that is pretty much the entire database. And then from, again, Ensemble uses NCBI's BLAST implementation, so that's Ensemble. BLAT is similar to BLAST but structured differently. Okay, it finds similarity in DNA and protein, but it needs an exact, which means it has to match those 11 MERS, right? If it doesn't match those 11 MERS, then you're not going to get it. So your query sequence is probably broken up into 11 MERS, and then each of those indices are matched against the sequence of interest, and then you can find the sequence. Okay, so again, the giving you the idea of is important. Now, there used to be something that I used to have, and I can't remember where it is. Let me see if I can find. Why don't you guys take a break, and we'll come back in about 10 minutes, and then I'll find out this other thing I was looking for anyway. All right, let's continue. Now, it turns out that I couldn't find where I had it. Maybe a different version of this, maybe a different version. And so, but there's a different way to look at it, right? So let's look at our web page. And I'm just going to give you two examples. So let's say I have this. I don't really care about the sequence I put. And the algorithm parameters are target sequence is 100, short queries. The mismatch is 2 for a match, 2 for a -3 for a mismatch. The gap, and now we're not using an affine penalty. We are using for example, it was, I think, 5 and 2 or 4 and 2, something like that. Now, if I went to, for example, a blast P, okay, then I can go in here and see what they're using a Blossom 62. See, now what happens is now you're using a -11 for a gap and -1 for an extension, right? And you're going to use the Blossom 62 matrix, and we'll see what that is, right? And so this is one way to look at it. I don't know what I did with that table. It used to be on the slide, so I don't know. But if we use the BLAST X, then you're still using, because you're looking at protein, and that is the exact same thing. What happens if you use a T-BLAST N and you're using a 62, and then, like, see, if you have a T-BLAST X, a nucleotide with a nucleotide, uh, then again you're using a different set of criteria. Okay, so again, this is another way to find out, in case, like, I actually don't have the table, which I should have. Let's take my pill. But there are other ways to find out what the defaults are. But it doesn't matter what the defaults are. You can introduce your own. Okay, so now we are looking at a methodology to compare proteins. Now, protein fall under a different category, because now you have and those are called as Blossom, two methodologies, Blossom and PAM. Blossom is something that's more used, PAM is not as used, but each of them has a slightly different approach, but the methodology is still the same. So the question is, how does one make a determination that that in a scoring way? Right now, I we talked about Blossom, right? Remember, we talked about the Blossom matrix when we did the and let me get out of this so we can go right to the beginning. And we did the Blossom matrix when we looked at this stuff, remember? So this was how we did it. And the question is, how did they come up with these numbers? So for example, if a um, glycine, okay, if a glycine matches with a glycine, how do I get 6? Okay, if a glycine aligns with a aspartic acid, a glycine with an aspartic acid, why do I get -1 as opposed to -3, or opposed to -6, or opposed to 7? And that is the crucial part of what we are doing here. And where do you get those numbers from, right? Remember, at the end of it, you're required to get a real score, and that is what we are looking for. So two methodologies. The PAM matrix was created by Margaret Dayhoff, and then you had the Heineckhoff, and Heineckhoff, don't know if they were related. They created the amino acid substitute. The PAM is point mutations. Okay, we'll come to what that A is. And Blossom is what is called a block substitution matrix. So we also saw that the Blossom 62 is typically used, but you can use other substitution matrices too. So for example, let's go back to that web page. Let me see where it is. Let's go back to this web page and say that if I wanted, let's say, the BLAST P, where I'm using the Blossom, and we'll see what that is. But I can use other Blossoms, see? And if you went there, you would see I could use Blossom. Let me highlight this. I can use PAM, I can use PAM 70, I can use PAM 250, I can use Blossom. So it Blossom 62 is the default, right? It's the default, but I can use PAM 2. And again, you can't see, like for some reason, the way it's rendering is you can't see the drop-down matrices, but but I can use all kinds of things. So the default, and you can see my mouse moving, and I'm going to click the Blossom 62 because that is the default. Okay, fine. Um, so if we have the Blossom matrix and the PAM, and these are the papers which come. So Blossom, you can see that it's not quite an acronym, obviously, but it's something that you can use, and you can see where the BL and the BLO and the SU and the M come from, the block substitution matrix. So how does this work? So now let's say Blossom 62. So you process a sample of protein. These might or might not belong to the same family. And so the question is, you are actually taking literally not experimental evidence, but experiential evidence where you're aligning sequences, right? Which have, so no more than that much similarity. So let's say you have a bunch of proteins and they do not have more than 62% similarity. Okay, that's important. No more than 62 sequences, and then you align them one against the other. They may or may not belong to the same family. You align them one over the each over the other, and then you see how many times you have a match, how many times you have a mismatch, and then you say how many times in this particular block do I have a glycine replaced by, and no gaps are allowed, okay? How many times a glycine is replaced by an alanine, or how many times a glycine is replaced by a tryptophan, or how many times a tryptophan is replaced by an arginine. Okay, so you're looking at each of these substitutions and you're actually trying to compute what are the probability in this particular group that you've decided is going to be your block. How many times is, and that's one of the reasons why when you look at the typical matrix, glycine matched aligned with the glycine is a really high score, because for a group that you think is that much similar, right? No more than 62%, for example, or no more than 80 for Blossom 80, or no more than, so no gaps, okay? So and the proteins have to be well known. In the sense, you have to know everything about it. They could belong to the family or not, but their alignments have to be known, cannot be more than that percentage. So Blossom 34 would be for something that whose alignment is not more than 34. The question is, why would you use Blossom 34? If you know that the proteins are not closely related, right? So then your alignment and your score and your calculations should be associated with a block, like a Blossom block, of things that are not very similar. If, on the other hand, you're looking to get a score for an alignment for something that's highly similar, then you might go with Blossom 80. But because there, at least we know that 80% of those are aligned properly. And then you will say how many times, so what is the probability of a glycine being replaced by something else, right? And that's kind of the point. So for each of the 20 amino acid, you calculate what is the log odd ratio. Okay, now if you say, well, what is the log odd ratio? And we'll come to that, right? So the question is, simply put in hand wavy ways, it is like saying, what is the probability of in one sequence a glycine, and then in another sequence in that same place you also have a glycine? That's going to be pretty high because these are well-known sequences. If, on the other hand, there is a replacement in the other sequence, though they're otherwise okay, what are the probability? And this probability is calculated as a log odd ratio. Now we'll see how those numbers are calculated, and the best way is to get an example. So let's say you have a fake illness. Let's call it COVID. So here's the way you look at it, right? And then we'll make that analogy to an alignment. Okay, so let's say you have let's say one of the symptoms of COVID is a bad cough. Okay, so exposure status: have you been exposed to COVID, and do you have a bad cough? Now, COVID, depending on what your political and sociological opinions are, had a whole bunch of things associated with it, right? So, some people had back pain, some people had fever, some people had cough, some people had cold, some people had intense body ache, some people had ear infection. So it kind of, for some weird reason, ran the entire gamut of things. Okay, fine. So let's say we just keep it simple and we'll say exposed to COVID and have a bad cough, right? So look at this. If you are exposed to COVID plus and have a bad cough, you come under the category of A. Okay, and uh, we'll bring the analogy to the amino acid alignments too, right? If you are exposed to COVID but do not have a bad cough, then you're in this category. If you do, and this is the best way, an odd ratio is the best way to look at it in a kind of in a statistically significant way, right? So, for example, if you have did not have if you were not exposed to COVID but had a bad cough, then you would fall under the category of C. And if you did not have, right, and were not exposed, then it's D. Now, before we go to see how that formula for the odd ratio is, first you do the odd ratio, then you calculate the log of odd ratio. But before that, so let's say, for example, let's say in amino acid position 5. Okay, in position 5, based on your block, based on the similarities, you say I expect it to be a glycine, and it is a glycine. I expect it to be a glycine. Okay, oops. I expect it to be I expect it to be a glycine, but it turns out it's an alanine. Now this could be many, right? Because glycine can be replaced by any of the 19. So this is calculated, and computationally you could kind of figure out a way to do it. Then the next place is not expected to be a glycine, but I find a glycine. And that's the way we look at it too. And that's why a log odd ratio is a pretty fair way of determining this. And then there's not a place for a glycine. I don't see a glycine, at least from a statistical standpoint, in position number 5, and I do not find a glycine. So all of these are taken into account in the calculation. So what happens therefore is you have, look and see, plus plus is A, and right? And so if you look at number of exposed cases, number of exposed non-cases, right, in the sense that no symptoms, versus the number of unexposed cases, cough but no exposure, and unexpected non-cases, if you calculate this, it's an easy way of doing it is A times D divided by B times C. And you see that here. Okay, and that's the way to do the log odd ratio. Similarly, they try to do it for and calculate, and that's why you see that big matrix, and they actually calculated those numbers, right? A non-glycine place either did not have a glycine, and a non um, one second please. So you can see exactly how you can draw that analogy. Now the question is, why do you use that? Now what we did was the calculation of OR, which is the odd ratio. So the question you have to ask yourself is, why are we talking about then the log odd ratio? So the question of the log odd ratio is a kind of gives you a simple example of why a log of that odd ratio is a lot more manageable. So think about it this way, right? If I have a range of numbers, right, and they range from 1, okay, another way, let's say you're doing a graph and on the x-axis you're doing some measurements, and the measurements range from 1 to 550 to 25,000 to 450,000. It's a big long range, right? It's very difficult to, in a linear way, take these numbers that are over such a big long range on, let's say, for example, on the x-axis. So what do? You say, let me take the log, because the log means anything from 0 to 1, 0 between 0 and 10, will be the number 1 point something, or between 10 and 100 will be 2 point something, right? It will be 1 point something. Between 0 and 10 it will be 0 point something, and from 100 to 1,000 it'll be 2 point something, and 1,000 plus will be 3 point something, right? So now what happens is, if you take the log of those terms, and if you want some sort of a linear characteristic to see how something behaves, taking the log of it is a lot better, especially if they go over a whole range. So let's take an example here, and I just got this straight out of Wikipedia, and it just kind of explains the point. So let's say, for example, you had 100 men, and on a weekend or a week, 90 drank, while in a sample of 100 women, only 20 drank. Now, let's not worry about the veracity of that, but let's just go with the numbers. Now, the odds of a man drinking wine are 90 to 10, or 9 is to 1. The odds of a woman drinking wine are 20 to 8, or 1 is to 4, right? So the odds ratio is calculated this way. So the odd ratio tells you that men are 36 times as much likely to drink wine as women are, right? That's based on the calculation we did. But if you use numbers like 36, etc., but depending on how you calculate the odd ratio, that means it's 4.5 times 90 over 20. That's another way of looking at it. But like if you say 90 over 20, it's like 4.5 times men drank as women, but the odd ratio, which is a statistically significant calculation, said men are 36% likely to drink as women, right? Which is in that particular block, a glycine is 6 times as much as replaceable by something else, right? By a glycine, whereas less zero point 0.1 something replaceable by something else. So what happens is, because sometimes the numbers are too big, right? You can take the ratio, for example, you can say that is 3.584 is the log odd ratio. So it becomes a more manageable number, and something that's not linear in scale, because then it's logarithmic in scale, can be linearized. And that's why you take the log odd ratio, because you're not quite sure of the range of numbers. Okay, so the Blossom 62 matrix, which is what we saw, and again, it's a matrix, it's a diagonal matrix, which means the you know cysteine replaced by a serine is -1, but a cysteine replaced by, or a serine replaced by a cysteine is also -1. And so in which case we don't really, it's kind of diagonalized, right? And so you can see the diagonal, because you would figure that the odd ratio of a the odd ratio of something being replaced by what is expected there is going to be a lot higher than the other numbers. Okay, so again, percentage conversions, which means when you have to kind of artificially create a block of known protein. They may or not belong to a family, but it cannot be more than, right? And so Blossom R could be Blossom 62, Blossom, like most common default, as we saw in the default in the BLAST searches, and Blossom 80, Blossom 45. So if you want to really get numbers associated with the alignment of things that are very closely related and a lot of alignment in that family, for example, then you go with the one that is more, and all these options are available. You typically use 62. The point accepted mutations, and so here's how we do it. So this is all already pre-created, right? It doesn't change. So you had 71 families of closely related protein. Now remember, the difference between PAM and Blossom is that the Blossom matrices are similar, but they do not have to be family. And therefore, because they come from the same family, a replacement is really called a mutation. Okay, because when it's in the family, you're looking to evolve, right? And you evolve by genetic mutations. So or differences are found because of mutation. 71 families of closely related proteins were used as a basis for PAM, and you created a phylogenetic tree. Now I put a question mark because we haven't studied it, but some of you have seen what a phylogenetic tree is, and we'll come to that soon. And you observed 1572 mutations, okay, positional mutations, and the sequences, so 85% similarity up to the phylogenetic tree, and highly targeted mutations were thus obtained, and this is how the evolutionary splits occurred. So if you really look at what is called a mutability, that's like the Blossom R, Okay, so the mutability indices were uh, how many times it was possible to mutate. So an asparagine was replaced mutable 134 times, and you get all these numbers. So a tryptophan, maybe because of its structure or its nature, the chances of it being replaced by something else are a lot less. And if you go here, you will find that also by conversely, right, which makes perfect sense. That is, when a tryptophan is aligned with a tryptophan, because the chances of it being replaced by something else are very little, that the tryptophan match with the tryptophan is actually pretty high. Okay, a glycine match with a glycine is also pretty high. A proline match with a proline is high, and that is because proline is very special, right? Proline is very special amino acid because it actually fuses with the alpha carbon change, and we'll come to that whenever we come to that particular. Okay, so the chances are, if it's hard to replace it with something else, that means that A value, the plus and the plus, is going to be really high. Okay, so the difference between Plosson, the one is allowed Blossom matrices alignment between evolutionary diversion. That means they can be family or not, whereas these were created based on specific families. PAM is good for global alignment based on local alignments. Uh, Alignments have higher similarity. So, and you'll see what I'm talking about here. Alignments have lower similarity than PAM. Mutations in the global alignment are very significant because of the evolutionary nature, which goes back to the families. Higher numbers in Blossom matrix denotes higher sequence similarity, and on the other hand, PAM is the opposite. So PAM 250 is used for more distant sequences than PAM 120. Blossom 80, the higher number, is related to closely related, because that means that the divergence has or the significance has cannot be more than 80. That means 80 is still a pretty high number, and therefore they are used for closely related sequences. Now, this is something I'm not going to touch into, but I'm just going to put it out here. What is multiple sequence? So basically, all the alignments that we have found are pairwise alignment, binary alignments, alignment between two sequences. So if you have your query sequence and BLAST, and you run it up, it aligns and aligns and aligns and aligns and aligns with all 25 billion or whatever number is possible, and then you have, oh, this aligned, this was the percentage, this was the significance, this was the number of percent alignment, this is which part, but it's always a pairwise alignment. There is also something called as a multiple sequence alignment, and you have many tools to do that. Mega, MSA, multiple sequence alignment, Clustal W, all these are multiple sequence alignment. So they will do more at the same time and then cluster all the alignments at the same time. Now we'll come to the last part of the topic for today, and that is what is called as cladistics. Remember, when we looked at PAM, they took 71 closely related families and they created a phylogenetic tree in order to basically track the mutations. So what is cladistics? Cladistics is a method of hypothesizing, right? Because what happens is, when you look at a clade or a cladogram, you look at a evolutionarily how something arose from its parent, and you say, well, they kind of look the same, right? So, and I'll give you an example, and irrespective of what your beliefs are, you look at a chimpanzee and you look at a gorilla, and then you look at a man. Now, a chimpanzee and a gorilla look a lot similar. That's different than a human being. But the one thing that a lot of these are, because they're bipeds, right? They can walk on two legs comfortably. On the other hand, most animals, yes, a dog might stand and beg for food and do all kinds of tricks, but it's not its natural posture. It's not its natural limb positioning, right? Whereas for humans, this is default. It's very difficult, very cumbersome for humans to walk on all fours, right? For obvious reasons, we're not constructed that way. And the ones that are close. So if you look at that, you will see the other thing you can also see is, kind of prehensile fingers, right? Prehensile fingers means that you're able to flex your fingers and able to hold stuff, right? And that most animals can't do it. For example, the ones with the cloven hooves, goats, etc. They just have hoofs, and hoofs are There's nothing they can't hold on to hooves. Yes, the flexibility, the open closing of the cleavage in the hooves allows ducks to kind of pretty much walk up vertical wall faces, um, but they're not prehensile, right? And even a dog's paws, for example, that end in claws, are basically end in claws, and they're evolutionarily designed for tearing and ripping and things like that, and therefore they're not designed for holding, right? So, you begin to hypothesize a relationship among organisms, and that organization which allows you to clump together certain physical behavioral characteristics is called a cladistics. Like other methods, you have to make some assumptions, right? Now you could basically say, well, those two animals look alike, therefore I would clump them together. But it's possible that if somebody does a comprehensive genetics or a genomic study, you'll say, well, I'm comparing the genes and they're nothing alike, right? So those are the assumptions you make. That is because that's why you're hypothesizing relationships. Is accepted as the best method for phylogenetic analysis. It provides an explicit and testable hypothesis of organismal relationships, right? So, for example, if you have these lemurs, they've got big eyes, and the big eyes means that they want to be able to take in and process light, and therefore they are nocturnal, and those big eyes are adaptable for taking in very small amounts of light and processing it into signals, so they have to have large eyes. An owl similarly has large eyes. It is also nocturnal, right? Same with bats. So the basic idea behind cladistics is that the members of a group share a common evolutionary history or are closely related, and these are related because we think of them as having similar characteristics, and those characteristics are called synapomorphies. Okay, now let's look at the definition of cladistics. So any group of organisms related by descent from a common ancestor. The first assumption is a general assumption made of all evolutionary biology. We all arose from something bifurcated. It essentially means that life arose on Earth only once, and therefore all organisms are related in some way or the other. Now, again, depending upon your belief systems, but this is kind of the conventional definition, right? So let's look at this one. There is a bifurcating pattern of cladogenesis, which means that organisms, like when you have a parent, it splits exactly into two offspring. And if those offspring have to split, then they split into two. Therefore, it is always bifurcating, okay, not trifurcating, or I'm going to make it into four groups. So that the change occurs in lineages over time. The characteristics of organisms change over time is the most important assumption in cladistics. It is only when characteristics change are we able to recognize different lineages or groups, or where the similarities break down, but some similarities are still discernible, in which case you say, oh, looks like that arose from that ancestor, doesn't look the same, but some of the synapomorphies are identifiable. Okay, now we looked at what a phylogenetic analysis is and what a cladogram versus a phylogenetic analysis is. Cladistics is useful for creating systems of classification. Cladistics predicts the properties of organisms, and cladistics helps to elucidate or understand mechanisms of evolution. What is the difference between a phylogenetic analysis? A phylogenetic analysis is a cladogram, except that it adds the extra feature of time. So if one says that something bifurcated into parents, daughters, in a phylogenetic analysis, it actually says, well, this particular bifurcation occurred over these many tens of thousands of years, or to go from one parent to several progeny over several generations of bifurcations took 2.5 million years. So the moment you add that timeline on the x-axis, so to speak, it becomes a cladogram, which is based purely a break on physical characteristics, similarities, or other synapomorphies. Phylogenetic analysis includes time. So let's take an example of what I'm talking about here. So different cladograms. So here's an arrangement or a taxon and what is called a monophyletic. a monophyletic, so all organisms are related. We saw that in terms of when we said, just you cannot use homologs. You have to use homolog in the right, in its kind of an accurate definition that is associated with a common ancestry, not necessarily, well, the sequences are alike and things like that, right? So let's look at here. A monophyletic taxon is the one that includes the most recent common ancestor or a group of organisms and all its descendants. So, okay, the most common ancestor, okay, that way. You won't mix this with this, okay? Then you have a paraphyletic. A paraphyletic includes the most common ancestor, but not all the descendants. So monophyletic and paraphyletic means, so for example, if you include A, then you've got to include everything that came from A. And if you did that, that was monophyletic. Okay, that means you can't just say I'm going to include this part, but not this part. Okay, so that monophyletic means all the common ancestors and including the that includes all the descendants. Okay, paraphyletic is, yes, common ancestor and the descendants, but not all, not necessarily all the descendants. And then you have a polyphyletic taxon, which does not include the common ancestor. So something like that. Okay, so this is monophyletic, as is this, right? And so this entire thing can also be monophyletic, but in this case, that's not what we are looking at, but at least it has to include the common ancestor and all the descendants that come from this ancestor. Now, here's an example of the cladograms of the apes or the monkeys, and so you have again everything is this is not very accurate, but it's a bifurcation. So lemurs and lorises are further down from humans. They are smaller, they are nocturnal, etc. Then you have tarsiers, New World monkeys, Old World monkeys, apes, and among the apes you've got bonobos and chimpanzees, gorillas, orangutan, gibbons, and siamangs, and then you have humans. Okay, similarly, you can have a phylogenetic tree, and it's a little incomplete here because there should be a kind of a timeline here. And so you will see that everything is necessarily a bifurcation, Nothing ever just splits into three. If it is, then it becomes a further descendant, and you have see humans from woolly monkey, lemurs, etc. And so a phylogenetic or evolutionary tree represents the evolutionary relationships among a set of organisms or group of organisms called taxa, which is the organization. The tips of the T represent the descendant species, and the nodes represent the common ancestors. The two descendants are called sisters, and the thing are called the parents. And of course, we look at time. So, in terms of the difference between phylogenetic trees and cladograms, very often they are used interchangeably. This is not necessarily accurate. A tree and its branches represent parent daughter, sister sister relationships. In a stricter sense, the lengths of the branches do not meet in terms of phylogeny, they are mainly connections, and you just say, well, and we understand that they belong to the same clade because of a shared synapomorphies. With phylogenies, the length of the branches do mean evolutionary times. Okay, that is very important. And the last slide in here is something obviously from you can see from the script, etc. That I got this from Wikipedia, but it came out of a paper, and you can see from the script that it's a very old paper, but it's not, you don't have to believe everything I say. I just give this for illustrative purposes. So for example, what you see here is, protozoa, it's the history of life, right? Single cellular organisms, and that split into, like tapeworms, flatworms, and things like that. And this is during the Lauric, the Cambrian, the Silurian period, and then you had the Paleozoic. But here's what becomes very interesting, right? You have a big evolution in terms of fishes, and each of these branches represents a species. Now, this is a very symbolic representation. You can't go sit there with a pen and count all of these and say, well, there were these many species, right? And then you had, but you see what happens is, as the fish begin to diminish, the amphibians show up, right? And then this is the Jurassic, where all the, you don't know whether they are birds or whether they are really, the large characteristics of reptiles. But then you see what happened. The fish, yes, they stay the same, and then the amphibians reduce. And as the amphibians reduce, the reptiles increase, right? And then the reptiles diminish. I mean, there's still traces of amphibia, traces of fish. Now, the fish are not that disturbed terribly because they belong in a different habitat, right, in water, and therefore they are not necessarily in competition with other branches of evolution. And then the reptiles reduced, and then the reptiles gave rise to birds, right? And the birds kind of same stable. But somewhere along the line, you had like the beginnings of a mammalia, right? Marsupials, etc. And then now we are in the age of mammals, and then the age of man. Now, what I see, you don't have to see, you don't have to agree, and I'm just throwing this out based on observation, based on nothing in terms of empiricism or scientific knowledge, is that it looks like the earth is the livable earth as we see it sustains only these many groups, right? So as one is ascending and stabilizing, the other is descending and stabilizing into a much smaller group. Now you can look at it in terms of evolutionary theory, and you can say, well, that is because there are far fewer, or they kind of died out, or the ones that were not fit enough did not survive, and therefore we have that kind of that some sort of a stasis here. Anyway, because we're talking about this, I just thought this was actually very interesting. One thing I realized, that in this particular lecture we have not we have not been interrupted. They didn't say, and I didn't even try too hard to get. So maybe that's something that we should think about. And I'll create a again, homework due by next. Oh, okay. So how do we know which to use? Does it matter in different situations or research questions? And so that was kind of answered. But Michaela, that's so yeah, you would, again, the default is, I haven't, whenever I've done this, I've just looked at Blossom 62 and not thought too much about it. But if you came from like something within a family, right? And depending upon the convergence or divergence of the family, you would have to just use PAM. If on the other hand you didn't care, there was nothing known, or nothing, you didn't care about like what particular family to look into, etc., then I would use Blossom. If it was something that you know very well, then you would use a higher version. If you didn't, then you would use a lower version. Okay. Okay, so again, homework due by 12 o'clock, or around lunchtime tomorrow, and I will send another homework your way. Please, 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 please. At first blush, the homeworks will seem really hard, but the expectation is that you will kind of buckle down and put your effort into it. Okay, and this is worth 30%, 50% of the grade. Homework is worth 50% of the grade, and then 25% for midterm and 25% for the finals. Okay, so if there are no more questions, you can continue the dialogue in emails, etc. But other than that, I'll just kind of stop the class now. Okay, bye.